Welcome to the channel. I'm Daniel from CMC Learning, and today I figured we'd go over a maths problem found in the second half of the Physics Aptitude Test. So Physics Aptitude Test, that would be sort of the university admissions test for Oxford Physics, and it has a nice mix of physics and maths problems. But here we're going to look at one of the maths problems in the second half of the paper, so around the 18th problem, and we're going to see how to solve it. So, upon first glance, we have a fraction, so e to the x plus 9 divided by e to the minus x plus 5, and this is going to be equal to 2, and we need to solve this for x. So as I'm sure you know, whenever a question is asking us to solve for x, they typically want your solution to look like this, so x is equal to something. So let's have a look what we can do. Already, just sort of off the top of our heads, there's not really much we can do in terms of this fraction. There's not much simplifying we can do. Had there not be this 9 and 5, maybe we could work with dividing these two terms, but we can't. So, and this is typically a good first step for most problems. I think what we should do is multiply out that denominator to the other side. So, let's see what we get. Get e to the x plus 9. This is going to be equal to 2 multiplied by this, which we can sort of expand out as such. Plus 10. Okay. Typically I should probably write this in. Okay. Now from here, in terms of collecting like terms, we can obviously move this 9 to the other side. I think that's also a good step. So let's do that. So let's take away 9 from both sides. E to the minus x. In this case, we have plus 1. So 10 minus 9. So right here, we obviously need to work with this sort of exponent term. In terms of factorizing, if we take out a factor of, for example, e to the x on both sides, that wouldn't really help us too much. Here we would have to sort of divide by that. We need to think of other ways to sort of manipulate this. And already it does look maybe a little bit intimidating. But there is sort of a mathematical trick that we can use. And this is something mostly referred to as a hidden quadratic, which any sort of A-level students out there probably should be quite familiar with this trick. Essentially what we have is a quadratic that hasn't yet sort of shown itself. The best way to do that is to rewrite this exponent, or the best way to see it is to rewrite that exponent, and let's see if it takes a familiar form. So here, if this is to the power of minus x, another way of writing that is just that sort of prefactor 2 divided by e to the power of x. And this is all plus 1. So here it's already sort of taking form a little bit. The identity that we should sort of be thinking of here is, what if we had some term? What if we had some term x, for example, equal to 5 over x plus 3. In this case, we can multiply the entire thing by x, so the left side and the right side. If we multiply that by x, we see that 5 over x just goes to 5, and this plus 3 goes to plus 3x. So here we can see this takes the form of a quadratic, so we have our x0 term, our x to the power of 1 term, and our x to the power of 2 term. So that's essentially what we need to do here. The only difference is, in this case, we have some sort of exponent term. If you want to be really precise with your maths, the best thing to do here, I would say, is introduce a substitution. I think that could help greatly. Let's introduce a substitution such that y, this new variable, is equal to e to the x. I think that will make things look quite a bit nicer, and we don't really have to deal with sort of figuring out exponent terms and whatnot. So what we're left with is y is equal to 2 over y plus 1. And from here, let's just multiply the entire thing. So the left-hand side and the right-hand side by y. And let's see where that takes us. So left-hand side, we have y squared is equal to 2 plus 1y. Now typically, as I'm sure you've been taught copious amounts of times, in order to solve these quadratic expressions, the best way to do it is to sort of have one side equal to 0. So let's do that by moving this 2 over, and also by moving this y. So what we should end up with in our expression is y squared minus y minus 2 is equal to 0. And keep in mind, all of this is with the substitution of e to the x as y. And we'll soon be able to substitute that back in order to get our final answer. But right now, we need to factorize this. The rules as such. Let's find some sort of pair of terms that product to make minus 2, but then sum to make negative 1. So this is a classic trick with quadratics, as I'm sure you know. In this case, we can factorize this as y minus 2 and a y plus 1. And this is all equal to 0, as we should remember. And as I'm sure you also know, what we have here are two solutions. So this entire thing here is equal to 0 if just one of these terms is equal to 0. So that allows us to write essentially two equations. We can go ahead and write those now. And those two equations are either y is equal to 2. We can see that that's when this bracket here goes to 0. And then just next to that, we also have y is equal to negative 1. So that's when that bracket on the right is equal to 0. What we should do now is resubstitute our terms in, or our term, sorry. In this case, we set y equal to e to the x. So let's go ahead and resubstitute that in. So here we have e to the x is equal to 2. And just below this, we have e to the x is equal to negative 1. So right off the bat here, we can probably see there are two solutions. But we do need to be careful with sort of one of these terms here, this term in this box here. In the Physics Aptitude Test, you do get a calculator. And I'm sure if someone were to figure out the sort of mathematical steps behind getting this answer, they'd probably find some sort of maths error. But let's have a look into why they actually find that maths error. Essentially, what e to the x equal to minus 1 is saying is, suppose I have some plot of y against e to the x, or sorry, e to the x against x. If we plot this up here, this is a characteristic curve that I think everyone should know at sort of A level. Here we have some exponential growth. And our intercept here is equal to 1. So this coordinate, if you will, is 0, 1. Now what this expression up here is saying is, find the value of x when e to the x is equal to negative 1. And as I'm sure you can see from this plot, sort of the negative 1 point on these axes is around here. We can call this graph, or this line, if you will, y is equal to negative 1. And here we can see that there is no sort of intercept. A good point to make is that in our e to the x graph, we have an asymptote at that y is equal to 0 line. So that's just a property of exponents. So here we can see that e to the x equal to negative 1 up here has no solutions. For any value of x. Essentially, it's impossible. So what we can do is rule out one of these answers to our quadratic. We no longer are concerned with that. What we are concerned with, however, is when e to the x is equal to 2. So if I were to plot that on my diagram here, that line would look something like this. So when I say e to the x is equal to 2, I'm interested in this sort of value of x here. So that intercept point. And if we have a look at sort of the algebraic maths to do these steps, we need to use our logarithms. Now, logarithms can, at least when you sort of first cover them in year 12 and 13, A-level, can be a bit tricky to grasp, but all they're really saying is, all they really are is a mathematical way to move around powers. It's quite useful. It's very good to be comfortable with all the ways to use logarithms. In the case that we're going to use them now, what we're going to do is we're going to apply a logarithm to both the left and right side as if it were some sort of operation, and in the end we should have some expression for x. What we want to choose here is something called the natural logarithm. So I'm sure you're familiar with ln. This represents, if I were to write this as ln y, for example, this is the same as the log with the base e of this term y. And another quick thing about logs, just to cover, not many people sort of know how to work with them in such a way. If I have something along the lines of log of a, or sorry, log base of a of b is equal to, in this case, let's call it c. What this is really saying is a to the power of c is equal to b. So this is how we work with logarithms, which I think is quite useful. If we look at our problem, we might need to use some of these identities. So let's have a look. We need to do e to the x equals 2. So let's apply the natural logarithm to both sides. It's equal to natural logarithm of 2. And one of those tricks that we were sort of mentioning before, if we really think about it, if we want to figure out what the natural logarithm of e to the x is, if we think more analytically and less sort of just by rules, here we're saying log base e of e to the x is equal to essentially our answer. We can call this capital A. This is what we want. So what this is basically saying is e to the power of a, if we remember our sort of log rules, e to the power of a is equal to e to the x. So in this case, we see that a has to be equal to x. That is the only solution for this expression here. So what we can do is rewrite that top step over there. Essentially, the natural log of e to the power of anything is just that power. So what we're left with is x is equal to the natural logarithm of 2. And that would be the solution to this problem. If we look all the way at the top, the only solution to this expression, given at the very, very top, almost there, there we go. If we were to put in x is equal to natural log of 2, we would get essentially 2 from this fraction here. It is definitely good to do some sort of physics aptitude practice, at least for next year. Being able to nail these maths marks are really important. So I hope that helped.